This will be the first part of the notes for section 7.2. And we're going to start finding some volumes as we revolve solids around some axes. So first of all, the whole concept of volume, going way back to elementary school when you were in about 4th grade, and you learned that to find the volume of a box or a rectangular prism or solid, that you do length times width times the height, is the exact same concept we apply to the cylinder or apply to a three-dimensional solid with parallel bases that has anything on the base. Really all you do is find the area of the bottom. That's what length times width is it's the area of the bottom or the area of the base, and you pull it up or give it its depth with the height. So likewise for a cylinder's volume, we find the area of the base, which is a circle, and we pull it up with the height. Or in this one, we find the area of the base, which is B1, and we pull it up with the height. And that thought process can be applied to any set of parallel bases. When I make a three-dimensional solid out of it, I simply need to find the area of the base and then give it its depth with the height. And so that concept gets applied on a much grander scale in calculus. We're not going to be doing length times width times height, but that whole area of the base times the height will be. So what I have here is like looks kind of like a loaf of bread, your favorite kind, cinnamon raisin. And we have these shapes on the bottom, which are basically every slice is the same shape. They're different sizes and different volumes, but they have the same shape. And if I were to cut them incredibly thin and have that height of every slice or its depth approach 0, and if I were to add them all up going out to infinity, what I would have is the volume of the entire solid. So let's move along and continue talking about our bread here. So I've got this bread that I'm slicing, and if I go shade in the face of this, this would be what we call the area of the base. And then here's the whole slice, and right here would be the height of the base. But when that height approaches 0 and it's along the x-axis, we call it change in x, and as it approaches 0, we call it a differential of x, or dx. So you can kind of see the integration kind of taking form here, because what we're going to do is we're going to find the volume of the entire loaf. Every slice, we take the area of the base and we multiply it by the height. This is just area of the base times the height. We're just going to call that height dx. And it works much better than water displacement, because that makes your bread soggy, and nobody likes soggy bread. Well, I kind of do actually, if it's dipped in some gravy, but anyway, let's continue on here. So what we're going to do is we're going to make those slices super thin, having delta x or dx approach 0, and we're going to do an infinite amount of them, and hence give birth to kind of our concept of the definite integral. So now let's take that concept and give a formula for it. So to find the volume, what we do is we take and we find the area of the base, back to 4th grade, length times width, times the height, length times width times height. We're going to slice it all up, add up all the slices as the heights approach 0. And this whole piece here is the definition of our definite integral. So really what we do is we add up all those slices, and depending on what the area of the base is, that'll kind of determine our volume. We're going to wait on example 1 because that one's the hardest one. So we're going to actually go over here and kind of get this laid out. So at first what we're going to do is we're going to have our solids, when we slice them, have circular cross sections. But they have a little tiny bit of depth to them also. So they tend to resemble really thin discs. And what we're going to do is create the solids by revolving about an axis, perpendicular, and our cross sections will always be circular, and we call them discs. Maybe with a C, maybe with a K, whatever floats your boat. But really, individually, they're little cylinders. They kind of look like pennies. So let's sketch out what we've got going here. We had split our sheet down the middle because we're going to talk about both dx and dy. And I'm going to go graph my absolute favorite function in the world that maybe goes like this. All right, and it's going to go from A out to B. And it's my favorite function. I don't know why. I just find it to be real pretty. All right, so what I'm going to do is I'm going to revolve that about the x-axis. And when I revolve it about the x-axis, what I picture is what we call a rectangular representative rectangle, a rectangular slice. And really it's so thin you can't see it, but I have to give it a little depth so you can see what's happening here. And I've got a little change in x going here. And I'm going to whip that thing around the x-axis. And in doing so, it's going to create this three-dimensional, really thin disc. And when I do all of them along the x-axis, what I'll have is a solid created. I'm going to do my original function a little thicker here so I don't lose track of it. But I'll have that symmetry going like that. And when I'm all done, I'll have a solid that looks like this. And again, it's kind of a pretty vase. The only problem with it is you can't put anything in it because it's completely dense and totally solid. But when I take one disc, one slice created by this thing going around here, what I have is what's basically a cylinder. And to find the volume of that cylinder, first thing I do is I get the area of the face of that cross section, and it's just a circle. It's just pi times its radius squared. Let's draw its radius on there so you can see it. And when I want to find the volume of that slice, all I need to do is give it its depth, which is dx. It's really a cylinder, pi r squared h. So pi r squared h, but h is actually a tiny little differential along the x-axis. So here's our formula for our integral. We are going to take and do the volume of every single one of those infinitely many cylindrical discs. And to do that, we do pi r squared h. And constants come out front, and I'm going to add them all up from A to B. And that gives us this formula. Now, the reason it says r of x dx is because when I go back up here, remember that right here is the point x, f of x. So my radius is really a function of x. See what I mean? It's actually f of x. So that's why it says r of x dx. So now let's go here. I'm going to give you my exact replica of my favorite function, which looked like this, went like that, from A to B. Well, now what I'm going to do is whip that sucker around the y-axis instead. And I'm going to do that really nice and bold here. And when I whip it around the y-axis, let's do it nice and neat. I'm going to have this symmetry going here. If I try to picture the three-dimensional solid it's going to make, I'll have a circle here and look like that. And it's really pretty. The problem is it's rock solid because every representative rectangle is completely solid. There's one of them right there. You draw your representative rectangle from the axis to the outer edge of the curve perpendicular to the axis of rotation, and that's kind of important. We can even call it perpendicular. How do you like that pun, huh? So anyway, we're going to run that out from A to B. So now what I'm going to be doing is basically having my cross sections be cut like this. And I'm going to have a little disc again, but my disc now has what we call a dy, or a differential, or a height, or a thickness along the y-axis. And it gets stabbed through by that vertical y-axis. However, I still find the volume of that cylinder the same way. It's still pi r squared for the area of the face. And the volume still pi r squared times the height. It's a cylinder. The difference is my height is not dx anymore, it is dy. So I'm going to be doing pi r squared h, and I'm going to integrate that, but now watch and take a look. I'm going to be integrating that from here up to here, I'm going to be doing these cross sections and all these cylindrical discs. So I'm going to be going from Y to Y. So if I call this the point A comma C, or even A comma F of A, and this B comma D, or B comma F of B, I'm going to be integrating up the y-axis with respect to y, where my radius is now a function of y. So let's go practice that and see how it goes. First and foremost, we need to get ourselves a really good sketch so we can see what's going on here. So my function, my f of x, is the square root of x, and that's just the shout out function. I'm also being bound by x is equal to 1, and I'm bound by this. So I'd go shade that in if I could shade nicely, and I'm going to be whipping that thing around the x-axis. So I draw my representative rectangle perpendicular to the axis of rotation. I note that my differential is on the x-axis. I picture this as being solid, and I'm going to whip that sucker around the x-axis, creating a thimble that I can't put my finger in because it's too dense. It's totally solid. There's no hole drilled into it. Every cross section, if I can start to slice that with a really good cheese cutter, every cross section is going to look like this. And so for me to integrate that thing, I have to integrate from x out to x, 0 out to 1. I'm going to just start making these slices and adding up all of these cylindrical discs. And when I do that, I do pi times r squared as a function of x dx. So let's go take a look at what r is as a function of x. Here's the radius represented here on my singular slice. That's my radius. In terms of the function, this point right here is the point, that point is a point x square root x. So my radius as a function of x is nice. It's just up to the square root of x. So normally I make you write it out like this. This is a dx problem. This is making a disk, and my radius is the square root of x. This is really good stuff to sort out before you even kind of set up your integral. If we were going, by the way, this way, don't draw this in your notes, but if we were, then when we draw our representative rectangle from the axis to the outer edge, perpendicular to the axis of symmetry, notice I'd have this gap here, and what I would end up getting is what we call a washer, because every one of those is going to have like a little hole in it, and we'll deal with that tomorrow. So everything today will be a disk problem. But my radius is the square root of x squared dx. Don't forget that squaring, and don't forget the pi out front. It's a really easy function to integrate because it's, 0 to 1, because it's just x dx, which would be x squared over 2 running from 0 to 1, which is just going to be pi over 2 minus 0 with our fundamental theorem of calculus. So that was kind of the first one. Let's go do 2 more, and then perhaps I'll go back and do that example 1 if I have time. Next one up, it looks similar to the last one, but it's not the same, so let's go get a good function on here. We are bound by y equals 1, so let's go up here. Y equals 1 is one of my functions. Y equals the square root of x is another one of my functions, and x equals 0. And I need to be bound by all of that, so I've got this, this, and this. And you should shade inside of here. I just can't shade very well on my smartboard. I suppose I could if I had the patience. Oh, I'll have patience. All right. So I'm going to take that, and I'm going to be whipping that around the line. Now this one says around y equals 1. I'm going to be whipping it that way. So you can kind of see what it's going to be making. It's going to go like this. Come down. I'm going to have a solid. It's going to look kind of like a Gulf tea with an extra fat head on it. But in order for me to determine the volume, I need a couple things. First of all, I draw my representative rectangle. It goes It goes from the axis of rotation to the outer edge of the curve. This needs to be drawn. You need to put the differential on there. You need to note that when you're going this way, there's no gap here with the line y equals 1, so it's going to be entirely solid. We're going to have discs, no holes drilled out. By that I mean that representative slice is all solid in there when you whip it out with that. This rectangle right here is that edge right there. It's a disk, it's dx, and the next thing I'll need to find is my radius. But let's go set this sucker up first. So I'm going to be integrating this way. That's when I'm drawing these vertical rectangles here. I could have made my representative slice here. I could make it anywhere. I need all of them. They need to be really thin. But anyway, I do pi times radius squared dx. The radius needs to be a function of x. My integration needs to go along the x-axis. So the question becomes, what is that radius? Let's go back up and take a peek. My radius is from the axis to the outer edge. It's that distance in black. Well, keep in mind, this point right here in black is the point x root x. So the square root of x is actually the height from here up to here. That's not what I want. I want this leftover gap between it and 1. So I'm going to have to take 1 and subtract off the square root of x to give me that piece right there. So my radius as a function of x is 1 minus root x. So here's my integral. I'm going to integrate from 0 to 1 pi r squared dx. And you can go ahead and math 9 that instead of doing it by hand. For time purposes, I'm going to move on. Example number 4. Let's go whip this sucker out. So I've got my favorite cubic function in the whole wide world, the parent function for cubics, y equals x cubed, going like this. I've got my favorite horizontal line through y equals 8. And I've got my favorite axis, x equals 0, aka the y-axiosis. I am bound by all of them. So you would shade this in. What am I revolving around? The y-axis. I'm going this way. Now, had I been going this way, when I draw my rectangle, kind of look, I'm going to erase it in just a second, but when I draw my rectangle, it's actually only solid from here to here, and then it's kind of open. So what that means is I have a hole that would be drilled out of my solid, and I would have what we call a washer. But because when I draw it, again, I'm going about the y-axis, my radius is always drawn perpendicular to the axis of rotation and out to the outer edge of the curve. And I can draw it anywhere. I can draw it there, I can draw it here. If you really want to have fun, draw it in here. But I just need one representative slice, because if I can get one of them, I got them all. Well, this is definitely dx. There's no gap here with the axis of rotation, so it's going to be a solid cylindrical disk. So this is a dx problem. It's going to make disks. I'm going to need to find my radius with respect to x once I set this up. So let's have at it. Mrs. LaRue did a naughty, didn't I? It said about the y-axis. Sorry, got to erase that. I changed the plans here. Sorry, I'm so sorry. All right, I need to go perpendicular to the axis. I said y-axis, I wrote y-axis, but then I did it with respect to y equals 8. So I'm going to be revolving here. So I'm drawing my representative rectangle perpendicular to the axis of rotation and out to the outer edge of the curve. This is a dy problem, and it's still disks. So this is dy, this is disks. And I need to find my radius with respect to y. Sorry about that. Anyway, let's integrate. I do pi r squared dy. R is a function of y. And I'm running up the y-axis. So my limits of integration are actually up from 0 all the way up to 8. I'm going to be whipping these rectangles around. It's going to create this solid right here. Again, it's going to be kind of another, like an acorn, completely solid. All right, it's getting kind of messy, but messy to you is pretty to me. It's going from 0 up to 8. And then I just need that radius as a function of y. So what we need to go over here and do is look at what this point is. Yes, on the curve it's x cubed. However, that's not what I want because I can't put an x in with dy and y limits. You can't have a variable mix. So I want my independent variable to be y, which is weird, but it's just thinking backwards. So if y is x cubed, then x is the cubed root of y. Well, that makes sense, right? Think of a point on that curve. On the curve, y equals x cubed is the point 2, 8, right? X, x cubed. But you could also say, no, 8's going in, and then you'd say, well, the cubed root of 8 comes out. So that's the cubed root of y right there. That's x as a function of y. Anywho, let's go plug that in. We'd have the cubed root of y squared dy, which becomes pi times the integral from 0 to 8. Remember, bottoms out, so the bottom of the fraction would be a 3 because that's on the outside of the radicand. And I like to say radicand. There we go, dy. And I could do this by hand if I had to. I don't want to, but I could. I would do my antiderivative, adding 1 disguised as 3 over 3, which would be 5/3, dividing by that, giving me a reciprocal effect, and I'm going to pull my constant out front, going from 0 up to 8. This would become 3/5 of pi times 8 to the 5/3 minus 0 to the 5/3. 8 to the 5/3, you might think, I can't do that in my head. Sure you can. Bottoms out, this is a cubed root of 8, which is 2 to the 5th power. 2 to the 5th power is 32. So when I'm all done, it looks like I got 94 pi-fifths. Fun, huh? I'd actually choose to math 9 it right here if I had my druthers. All right, so I think what I am going to do is stop here. That's enough to get you going. I am not going to do that other example. I did it in class, but I'm not going to do it for video notes. Have a good one.